Greetings. Your Extrasolar Planets lab was written probably about 10 years ago at a time when it had not yet been fashionable or become fashionable to shorten the word extrasolar to just exo, or exoplanet, I should say. Extrasolar meaning outside our solar system. So the word exoplanet just means a planet that's outside our solar system. And even by 2015, I believe, there were something like 4,000 planets that had been confirmed to exist outside our solar system. And when you guys were little kids, and certainly when I was a youngster, it was not at all certain whether most stars in the galaxy had their own planets. It may have been speculated that it was typical for all stars to have planets the way our sun has 8 or 9 planets. And now I believe it's just accepted that that's the rule, not the exception. And many of those first planets were discovered by this telescope here, the Kepler Telescope, which is a NASA telescope. It's been retired. I think it's still in orbit. I think it's a trailing Earth orbit, so it's going around the sun at the same distance that we go around the sun. And much of the data had been collected by 2015, or maybe even processed by 2015. It looks to me like a giant tube of lipstick. Now, this telescope discovered its planets using the transit method, which I'll discuss in another video. Here's what they call a Kepler orrery. That's a hard word for me to say, orrery. It's just a visualization of all the stars which have been discovered to have planets moving around them. Where's the play button on this thing? So you can see the date updating in the upper right corner. Oh, come on. I'm an amateur PowerPoint user. Okay, so obviously this is not to scale. It's just showing you the relative position of all the stars looked at by Kepler and discovered to have planets orbiting them. It's a whole lot of planets, and the number is even bigger now. In fact, I just looked this up. You can visit a NASA webpage at any time and get updated information about the current number of exoplanets that have been confirmed. So now we're up at 4,300. Look how recent that date is for those of you in fall 2020. And then the newest space mission out there for discovering new exoplanets, Transiting Exoplanet Survey something or other, TESS for short, which I have an easy time remembering because that's my sister's name. But look at that, over 2,000 candidates. So you can expect many more planets to be confirmed in the coming years. Bookmark that site if you're interested, eh? Now, some of the earliest discoveries are even more, well, I'm not going to say mind-blowing, but see, the methods that are used primarily are actually pretty sensible when you learn how it works. It's something you may have even thought of on your own if you have been tasked with coming up with a way of detecting planets. But believe it or not, planets have actually been directly photographed. The methods we're going to look at in this lab are like indirect detection. But planets have been directly detected. So here's the Keck Observatory on the top of Mauna Kea in Hawaii. And this was an image taken by the Keck telescopes of exoplanets orbiting their host star. So the star has been blocked out so that its light doesn't obscure the image. But at the center of the solar system is a faraway star, and here are some giant, probably gaseous planets like Jupiter orbiting that star. And you can see how far they are. They're telling us that this distance, the scale here, this is 20 astronomical units. And that's about how far planet D is from its star. So 20 astronomical units, that's 20 times the distance between the Earth and the Sun. Now, this is not a visible light photograph. I believe, like I said, it's infrared, which is just a color that your eye does not detect. It's a color beyond red, one that your skin actually absorbs really effectively. So there do exist actual photographs of faraway planets, and we can probably expect more of those after some of these ginormous telescopes get constructed. Here's an example. I don't remember what ALMA stands for, but it's down in Chile in the Atacama Desert. It's an array of large radio satellites that are acting together as one giant telescope. And the ALMA array has actually produced high-resolution images of solar systems in formation. So what you're looking at here is not a bunch of galaxies. And this is just a collage of images that have been placed side by side, but each of these is a faraway solar system. So rather than 200 billion stars, like the Milky Way, for instance, we're looking at just one star in the center and a disk of gas and dust surrounding that star. And from that disk of gas and dust will accrete planets. In fact, you can see some of these are more mature and far along in their development than others because many of the planets have already formed and cleared out their orbital paths. So images like this, as of 2020, did not exist 10 years ago. I think the earliest one was maybe 2014, and that's this one right here. And you can only get pictures like this with ginormous telescopes. So here's another way that the existence of exoplanets can be directly imaged. You wouldn't see the structure here if it were not for planets forming around stars. These are also from the ALMA array. Okay, that's a photograph of those telescopes down in Chile. And again, even though each one of them is, I don't know the diameter, it's probably the size of a small house, but when you get them all together like this, it's kind of like one ginormous telescope. Now, the method of detection that you'll be looking at in the first part of your lab, and the one that I'm going to talk about in this video, is the radial velocity or Doppler shift method. And a good place to start would be the Doppler shift for sound waves, with which you're all familiar. Okay, that wasn't real pronounced because the ambulance isn't moving that quickly, but you'll notice that as the ambulance was approaching the camera, the pitch of the siren sounded a little high, and as it passed and then receded from the camera, then the pitch dropped a little lower. And when it comes to sound waves, the pitch the frequency of the sound has to do with how many crests of the sound wave are hitting your eardrum per second. And that'll make more sense when we look at a simulation here. Here's my favorite demonstration of the Doppler effect for sound wave. Now, the Doppler shift is a phenomenon that's present for any type of wave. I almost said wave phenomenon. I'm abusing the word phenomenon there. But for now, let's think about water waves. This could be a little ducky in a pond flapping its wings. And every time it flaps its wings, it makes one of these little circular wave fronts that travels outwards. Or it could be sound waves, like the trumpet. So the air column within the trumpet is vibrating, and those vibrations travel outwards. And let's say the dark bands here represent where the air pressure is slightly greater, and the light bands indicate where the air pressure is slightly less than normal. So you've got these ripples of air pressure. If we're talking about light waves, it's not obvious to most of us, well, any of us really, until we've studied it, that light also exhibits wave behavior. And then it's a lot less obvious what exactly is waving. Well, it's these things called electric and magnetic fields. We don't need to know the details for this lab, but suffice it to say that light is a wave, and you can also experience or observe the Doppler effect with light waves. So, by the way, this website's awesome, falstad.com. They have a lot of fun simulations. or very instructive simulation. So let's go down to Doppler Effect 1. So now the source is moving. And this red circle indicates the observer. So this is like your eardrum, perceiving the sound waves striking your eardrum. Now let me replay that. And you'll notice that right now, oops, for the first few seconds, the source is approaching the observer. And do you see how the wave fronts are kind of bunched up? Down here, look at this number that's hovering around 300. That would be the number of waves hitting the eardrum per second. And now that the source has passed the observer, this is like the ambulance going off in the other direction, you can see that now the wave fronts are more spread out and fewer of them are striking the eardrum per second. So that's why the frequency dropped down below 300. Okay, now it's bounced back and it's doing the opposite. So let's just continue to watch. See how the waves have stretched out now? So this is the source of sound moving away from the observer. Once it switches direction, now the waves are bunched up and more of them strike the eardrum per second and the pitch has gone back up. So that's a great way to visualize the Doppler effect. Again, it works for, or it's something you can observe with sound waves, water waves, and most importantly for us, light waves. That includes radio waves because radio waves are much like light waves. In fact, there's really no qualitative difference between the two. It's just that your eyeball can only see certain types of electromagnetic waves, which we call visible light. But there's all these light waves outside that range, radio waves, infrared, ultraviolet. So here's a graphic of the electromagnetic spectrum that you can find on the web or any book practically on this subject. These are the waves that we see. Let's not worry about wavelengths, but you just need to know that blue light, violet light, those are the shortest electromagnetic waves that we can see, and red light has the longest wavelength. Any electromagnetic wave, or I could just say light wave, that has a wavelength even longer than this would be invisible to your eye. It's beyond red, so we call it infrared, or is that under red? And any wavelength that's shorter than what we see on the violet end of the spectrum would be called ultraviolet. Again, not visible to your eye, but there are insects and maybe even non-insects that can see those colors. And don't take this distance literally here, because on your screen, this is like what, an inch? The actual wavelength of light is many times smaller. It's smaller than the width of your hair. Something like 10 times or 100 times smaller than that. So here's somebody else's little animation of the Doppler shift for light waves. Instead of an ambulance moving towards you or away from you whilst emitting sound waves, now we're looking at a star moving towards you or away from you, emitting light waves.
For an observer, if a star was moving towards them, the light waves produced by the star in front of the star would be compressed together, giving high-frequency light waves. High-frequency visible light is of a blue colour, so we call this blue shift. If a star is moving away from an observer, the light waves produced behind the star would be stretched out, and this would give low-frequency light waves, and low-frequency visible light is of a red colour. This can be seen with stars when we look out in the universe, that the stars have...
Okay, I think the sound was not synchronized there with the graphic, but hopefully you get the idea. It's kind of a crazy thought, but if somebody had, let's say, a red laser pen, and they were shining it into your eye, let's say a low wattage laser pen that's not going to hurt your eye, if such a thing exists. If they were flying towards your face in a spaceship and actually moving fast enough, that red laser light might look blue. You'd have to go really fast to achieve that kind of Doppler shift. Speeds comparable to the speed of light or half the speed of light. It's easy to calculate, but just know that the effect is there. It's something we don't normally notice. Now, this explanation here is going to mention the spectra of gas molecules. That doesn't concern us here. Let's just focus on the fact that light can be shifted towards the red or blue end of the spectrum.
Scientists can also use spectral lines to work out whether a galaxy, like this, is moving towards the Earth or away from the Earth. Let's compare two sets of spectral lines for this galaxy as we expect them to appear. The positions of the spectral lines are based on the absorption lines for various elements as they have been measured in laboratories on Earth. If the galaxy was moving towards an observer on the Earth, the spectral lines would shift to the blue end of the spectrum. This is known as a blue shift. If the galaxy was moving away from an observer on the Earth, the spectral lines would shift to the red end of the spectrum. This is known as a red shift.
Okay, so you just need to know that when we're looking at an object out in space that emits light, namely a star for this lab, if it's moving away from us or towards us, the colors emitted by that star will be shifted in frequency. They'll look a little bit different. Now, again, it's not something you may be able to detect with your eye, but using instruments, measuring devices, that can be detected. And it shouldn't come as too much of a surprise that we have that capability, because many of you have been written speeding tickets with this technology. It's really the same technology that's used to determine if a vehicle is exceeding the speed limit. So the radar gun, I forget what radar stands for, but it emits, let me get my laser pointer. The radar gun emits waves of a particular frequency. Those are radio waves, so they're much like visible light waves, but the wavelength is far too long to be seen by your eyeball. But they're essentially the same as visible light waves. They then strike a vehicle, let's say a vehicle that's approaching the police car, and when those waves are reflected, they're shifted in frequency. Again, this is like just a moment ago, the graphic of the galaxy approaching planet Earth. Well, this time it's a vehicle approaching the police car, and that vehicle is reflecting the radio wave, but the new frequency of the radio wave, I'm trying not to use the word reflects twice, but it reflects the fact that the vehicle is approaching. It doesn't really matter that it's reflection. It might as well be, it's like the car's got its own radio transmitter. And because the car is moving towards the police vehicle, the radio waves are shifted towards shorter wavelengths. And I'm realizing now that these colors are totally backwards for our purposes. It really should be that the cop is emitting a red wave and the wave gets reflected as blue, because do you see how what they've drawn as a red wave actually has a shorter wavelength? That would correspond to blue light. Blue light has a shorter wavelength than red. So if I had made this picture, I would have reversed the colors. Okay, so in this example, police guns use, or at least the older ones, use radio waves. I think they actually have laser guns now. They use LiDAR instead of radar. But you'll notice in each of these photographs, the radar gun is pointed down the road. So the radio waves are going parallel to the road, directly at the vehicles. You don't see in any of these pictures the cop off to the side of the road so that the radio waves are striking the car perpendicularly. And this is something you need to understand in order to do this lab. So here's the cop car, and let's imagine that this red sports car, I picked red because they're always the ones that speed, right? Let's say he or she's moving in a circular path, and right at this moment, we know that the velocity of the car is tangent to the circle, so it's off in this direction. That means that the car's direction of motion is perpendicular to the line of sight from the cop car to the speeding vehicle. And in this configuration, it would be impossible for the cop to detect any speeding. The vehicle must be going towards the cop car or away from the cop car. So right now, this tangential velocity doesn't work as far as the radar gun is concerned. In this case, the car is going at the vehicle, and we call this a radial velocity. Radial because this is the radius of the circle. We know that the radius of a circle terminates at the center of the circle. So if something is moving towards the observer, that would be a purely radial velocity. And I say negative because the convention that your lab manual uses is a radial velocity is considered negative if the source of waves is moving towards you, towards the observer. If it's moving away, like in this picture, that would be considered a positive radial velocity. And you want to try to memorize that. Something moving away, that's a positive radial velocity. Now, the general motion of something you look at in the sky is a combination of those two things. So, in this example, if the vehicle that's being watched by the cop is moving in this direction, we can decompose that velocity into components. One component is directly towards the police officer. That's a negative radial velocity. And the other component is tangent. So this component of the velocity would not be detected by the radar gun. The Doppler shift can only be used if we're talking about velocity directly towards or away from the observer. Now, you know that you can be busted for speeding even if you're going just 5 to 10 miles per hour over the speed limit. That's a speed difference that's easily detected by a radar gun. And so it should be no surprise that the same technology can even detect whether the edge of a star is turning towards us or turning away. So this is obviously much sped up, but here's some video of the sun rotating, and you can see how the left side of the sun is moving towards us due to the rotation, and the right side is moving away. So that would be considered a positive radial velocity on the right and a negative on the left. And the magnitude of that speed towards or away from the camera here, I don't know what that speed is, but even if it's just a few miles per hour, it can definitely be detected by a technology similar to a radar gun. Here's another awesome simulation from the PhET website. That's Physics Education Technology. And this will show us the mutual orbiting of a star and its one planet around their common center of mass. So normally you think of a planet as orbiting a sun, but really they both orbit. They're both making elliptical orbits around one special point called their center of mass, which is like the balance point. So you can see the planet is tracing out a much larger ellipse, but the sun does wobble. Now, in our solar system, the motion of the sun is more complicated because it's being tugged in a bunch of different directions by Jupiter, Saturn, etc. But in a binary system of just one star and one planet, this is what you've got. Now, why was I showing you this? Right, the whole idea is, what if planet Earth is way over here? And we're watching the light coming at us from this star. Much like a cop over here with his radar gun watching the motion of that speeding red vehicle. So right about here, when the sun gets right here, or the star, that star is moving towards planet Earth, and when the star is down here at the bottom of its orbit, at that point it's moving away. So there would be a radial velocity, positive or negative, that could be detected by this Doppler shift method. Now, it doesn't work for the planet, unfortunately, because planets don't emit their own light. They only reflect the light from the star, and that light is usually too dim to be detected with the instruments. Now, something you'll need to know for the very first page of the lab. Surprisingly enough, questions 1 and 2 are two of the most difficult questions in the entire lab because you can't use a simulator to answer them. And that's why I'm showing you this simulator. Can I slow this down? Yeah, here is the observation that you need to correctly answer questions 1 and 2. Notice that the star and the planet are always on opposite sides of the center of mass. So the center of mass would be somewhere on the line joining these two, and it's going to be close to the star because the star is so much more massive. So let's just say that the center of mass is, that's kind of tough, right about here. Do you see how the sun is on the direct opposite side from the planet? And that's going to be true at any time. So again, if the center of mass is right here, they are on opposite sides. And not only that, but their velocities are always opposite. So let me start at a convenient place right about there. Okay, so at this moment, The sun or the star is going off in that direction, and the planet is going off in that direction. One velocity is to the left, one is to the right. They're opposite. Same is true right there. Right now, the star is going down the page, and the planet is going up the page. At any instant in time, their velocities are always opposite. And you're going to use that fact to answer questions 1 and 2 on the first page of the lab. So here is that first page. And what they give you here is a graph of the star's radial velocity in time. And you have to read this carefully to discover that both graphs show the radial velocity for the star. But in the top part, you're supposed to label the various positions of the star on this diagram. And in the bottom part, you're supposed to label the various positions of the planet. So I'm just going to get you started here. Now, when we look at the graph here, let me just trace it out. Right now, the radial velocity of the star is negative. Now it's 0. Now it's positive. Now it's 0 again. And now it's negative. So let's pretend that planet Earth is over here. And we're looking towards the star. And I'm going to... Actually, I happen to have it paused at the perfect, almost the perfect time. Right now, when I'm looking at the star from planet Earth, the star is currently going up the page. Up the page is neither towards the Earth or away. So we would not be able to detect any Doppler shift at that moment in time from the light from the star. So that would actually correspond to position A on the graph, because that's 0 radial velocity. Yes, there's a tangent velocity, but that's neither towards nor away from the Earth. Now, just a moment later, the star is going to be on the top of its elliptical orbit, moving to the right. And remember the convention, away from the Earth is positive. So to the right would be away from Earth, if Earth is over here, and that would be part B. So if we look at the picture here, sure enough, they're saying the view from the Earth. So we're looking this way to see the star. Oh, and you know what? They've actually got the star going around the other direction. Okay. I don't know how to switch that in the simulation here. So in this picture, the star is going counterclockwise. So when it gets to the point at the bottom right here, that's when the star is moving this way to the right across the page. That would be a positive radial velocity. So I'm just giving you that first answer. This position right here corresponds to position B on the radial velocity versus time graph. So you would label this with a B, because that's when the star is going that way, away from Earth. Now, to answer the same question down here, we can now label the planet's position, because remember, when the star is on this side of the center of mass would be basically the center here. That's when the planet would have to be on the other side, going to the left. So again, when the star is here, moving to the right, the planet would have to be here, moving to the left. So you might as well do it in pairs. I know that when the star is here, the planet would have to be here, moving to the left. See how the arrow indicates that the planet is going around counterclockwise as well? I believe I've done that correctly. In fact, I'm going to pause and make sure I'm giving you the right answer. But I would just go ahead and label this point also as B. Yeah, that checks out. So if you're struggling with this, you're not alone. Like I said, this is one of the most challenging parts of this lab. And it's just the first page. How about we do just one more? So since the planet's going around like this, can we do this in the simulation? Yeah, okay, so the star is moving counterclockwise. So I'm going to pause right there. And you can see that when the star is right here, it's moving up the page, which is neither towards nor away. So that would have to be a radial velocity of 0. That's probably position C on the graph. And you'll notice that when the star is on the right side of the center, moving up, the planet is on the left side of its orbit, moving down. So over here is when the planet would be at position C. So I've given you almost half the answers there. I think you can figure out the rest for those questions. Also, I should point out now that if you've taken trigonometry at some point in high school, or pre-calculus or algebra 2, you probably learned about sine and cosine. So this wavy shape is basically sine or cosine. You could just call it a sinusoid, which captures the curvature of both of those graphs. Or you can say it's sinusoidal. So if at any point in the lab they ask about the shape of a graph, if it looks like that, you can say it's sinusoidal. Now it's time to move on to the Radial Velocity Simulator, but before we do that, I will remind you of Kepler's first law, which says that the planets move in elliptical orbits about their host star. Now, as cool as this simulation is, it's actually inaccurate because it shows the planet moving at constant speed around its star. We know from Kepler's second law, equal areas and equal times, that when a planet gets close to the sun, it's moving faster. So this planet should really be whipping around when it's at the so-called perihelion. But otherwise, this simulation is pretty awesome. Okay, now there's a couple quantities introduced in this lab that you almost certainly didn't talk about in your lecture because it's kind of esoteric. So when you look into the night sky, supposing you had incredible vision and you could actually zoom in and witness all these planets moving around the various stars, each of those solar systems is going to be in some arbitrary orientation. So here's an example. Suppose Earth is off in this direction. So when you look at this star, rather than, because this is your line of sight, rather than the planet orbiting in a plane perpendicular to the line of sight, in this case, it's not perpendicular. So this angle between what I'll call the normal line, if you're not familiar with that term, see here's the plane of the planet's orbit. Just imagine passing a sheet of paper through this orbital path. And here's a line that's, quote, normal to that plane, basically perpendicular. The direction between that normal line and the line of sight with Earth, that's called the inclination. And that inclination features in all these problems using the radial velocity simulator. So let's look at the simulator now. Okay, let me reset this thing. Okay, the first thing we should mess around with here is clicking on the screen and looking at things from different angles. You really should spend some time just poking around with the various sliding bars to figure out what everything is for. Let's look at this arrow, this yellow arrow that says Earth View. It's a shame I can't zoom out here. But do you see that they're indicating Earth would be way off to the left somewhere? And that means in order to see this solar system, you'd have to look in this direction, almost like you're looking at the edge of the plane of the orbit. So that would be an inclination of 90. Remember, we measure the inclination as the direction between the line of sight and the normal or perpendicular line to the plane of the planet's orbit. And that angle right now you'll see is 90. So if I drag this down to 0, there we go. If the Earth was, way off in this direction, then your line of sight would be perpendicular to that solar system. And that means your line of sight would be in the same direction as the so-called normal line. So the angle between those two directions would be 0. So inclination of 0 corresponds to looking kind of like face on. Can I say that? Edge on versus face on at the solar system. And the advantage of that would be if you had some super powerful telescope, much like the picture I showed you from the Keck Observatory, you'd have an awesome view of the planet actually going around the star. It would actually look like this. Let me start the animation. If your inclination was 0, this is what you might expect to see. However, for using the Doppler Shift method of detection, it's useless. Do you see that in this configuration or orientation, this planet is never actually moving towards you or away from you? Yes, there's a tangent velocity, but there's no radial velocity. So just think back to the cop car and the radar gun. This is no good for using the Doppler Shift method. On the other hand, if the inclination was 90, which was actually the default, so let me put the camera in the same place that the Earth is. This is ideal for using the Doppler Shift method because right here, that's when the planet is coming out of the screen, so to speak, directly at you. And then on the right side, when it gets there, so again, directly at you, and then here it's going directly away. Now, when it gets to the middle, it's actually just going to the right. And when it gets to the back, it's going to the left, neither towards nor away from you. And that's what we're seeing in the behavior of this graph over here. That's this sinusoid. So let me see if I can pause it right here. Okay, at this moment in time, see Earth's over here. The planet is moving that way towards the Earth. That's when it's got its greatest radial velocity in the negative direction. Oh, and it looks like this simulator uses the opposite convention. Darn it, because remember in your lab handout it says radial velocity away from you is positive. Well, here, yeah, I'm going to wait for this planet to come back around. Right here is where the radial velocity is towards Earth, and they've actually got that as a positive velocity. Okay, that's no big deal. They're just using the opposite convention. But look at that. If I just hover over the top there, 28 meters per second. You could also sort of read that off of the vertical axis here. It's a number greater than 25 and less than 30. So 28 meters per second, that's like 65, 70 miles per hour, which is a speed, of course, you can detect with a radar gun. So it's totally conceivable that astronomers can do this as well. So I'm looking at, on page 3 of 10 in your lab, question 3, describe the radial velocity curve. Well, I would look at that and just say it's sinusoidal. What's its shape? Yeah, sinusoidal. What's its amplitude? Okay, the amplitude is just the height. Do you see how, let me, okay, when the planet is right here, it's sort of coming towards Earth, but it's also sort of going sideways. So its radial velocity is not at a maximum. And you can see that right here. Now at the radial velocity is only 17. The amplitude refers to the highest attained value of the radial velocity. So you can just hover over the top of the curve and read that number off, 28, 28 and a half, close enough. What's the orbital period? Well, that's easy. They actually just give that to you. Yeah, that is not a number that you would read off of here. Phase is something a little different, and I don't think we need to worry about that. So the period is just something you would read off the screen right there. Now, 365 days is a familiar number, right? And the reason that happens is because if you look down here at the presets, this solar system is set so that the planet mass is 1 times the mass of Jupiter. The size of the orbit, the semi-major axis, is 1 astronomical unit. So what they've done is place a Jupiter mass planet at the same distance from the sun that planet Earth is from the sun. And then the star itself is given a mass of 1 times the mass of the sun. And we know that if you put a planet 1 astronomical unit from a star that's the same mass as the sun, it'll take 365 days to go around. It actually doesn't matter how massive the planet is, whether it's Jupiter, Earth, the moon. If you put any planet at that same distance from the sun, it'll take the same amount of time, which is 365 days. Now notice if I make the star more massive, so a more massive star, twice the mass of the sun, would pull harder on planet Earth, and now that planet would whip around faster. You can see the period is now less than 365 days. So there's a number of things that will affect the period of the motion. There's the mass of the star. There's also the size of the orbit. Doesn't it seem reasonable that if I make the orbit bigger, it will take longer for the planet to go around? So now at 10 astronomical units, look at that, it takes over 8,000 days to go around that star. But if I change the mass of the planet, nothing's going to change. Watch this number. I'll drag the mass of the planet around, no change. Now, interestingly, it does affect the amplitude of the speeds. So let me pick another question or two from this section, the radial velocity section. Okay, I just realized I made a mistake a moment ago in speaking about the convention with the positive or negative. So this, remember, only the light from a star is bright enough to be detected. So we're looking at a graph of the star's radial velocity versus time. Now let me drastically increase the mass of the planet, and I will decrease the mass of the star. So the planet's now big enough to make this star wobble significantly. And I'm going to pause right here again. So at this moment in time, the planet's coming out of the screen. The star would be going, I shouldn't say out of the screen. Well, unless I do it like this, yeah. So at this moment in time, the planet's coming out of the screen. The star is going into the screen, which would be away from Earth. That's why it's got its maximum positive velocity. Now, in number 5 in your lab, how is the amplitude of the radial velocity curve affected by increasing the star mass? Well, think about it. The more massive the star is, the harder it is to move. Even if this is a very large planet like Jupiter, it's difficult to shove around a massive planet. So right now the amplitude of the, because my planet's so big, the amplitude of the star's radial velocity is, what is this, a little over 1,400 meters per second. But if I make the star more massive, meaning it's more difficult to shake around, it's the little orbit that it's describing should be smaller. And as a result, the star has a lower radial velocity at any moment in time. So if I put this back into, yeah, now it's still wobbling, but not as much. And as a result, you can see the amplitude decreased. So basically, the more massive the star is compared to the planet, the harder it is for gravity to shake that star around, and the amplitude of its radial velocity curve will decrease. Okay, so let me talk some more about the relation between the amplitude of the radial velocity curve and the inclination. So again, for using the Doppler Shift method, this is the most ideal possible inclination. You would like to be looking at a solar system edge on, so you can really see the effect of the planet coming at you, or really it's the star, right? It's the star's light that we're looking at. Now, if you happen to be unlucky and your inclination is more like that, so here's us actually looking towards the solar system. I don't know if you can tell, but the orbit is tilted slightly toward us, so there's a little bit of the planet coming at us and going away from us. Same would then be true of the star. But do you see how much lower the amplitude of the radial velocity curve is? Now it's barely 13, whereas before, whereas before it was up past 30. So the farther your inclination gets from 90, the weaker that curve gets. Again, 90 is the best you can hope for, because then the star and the planet are both coming out of the screen, into the screen. But if you're at 0 inclination, meaning your line of sight is like this, it's hopeless. The star and the planet will never be coming at you or going away from you. And that's why this curve has now become flat. So those observations will help you answer, for instance, questions 7 and 8 in the lab. Okay, now for questions 9 and 10, I've gone back to the preset option A. And this is an inclination of 90, so best possible scenario for using the Doppler Shift method. And the star's radial velocity curve has an amplitude of 30. So what I'm going to do is tilt the inclination back towards 0 so that the radial velocity decreases. You know, it becomes a weaker effect. So if you're looking from this direction, yeah, it's not worst case scenario like this would be, and it's not best case scenario like this would be. It's somewhere in the middle. So right here, the planet is kind of coming out of the screen, and so would the star be coming out of the screen or going into the screen. So you will detect some Doppler shift. There is some movement towards or away from the camera, so to speak. But it's not as good as it was before, and that's why the amplitude has now decreased to 20. So you could say that for a particular solar system, the closer the inclination is to 0, the less amplitude you're going to see in the radial velocity curve. Now, what happens if we now make the planet more massive? Remember, a more massive planet would tug harder on the star and increase the star's, or the size of the star's little orbit, and that means it's going to be whipping around at a greater speed. So let me see if I increase the mass of the planet. Here we go. Instead of 1 times the mass of Jupiter, and watch what happens here. Currently, we're at an amplitude of a little over 20. I'm going to drag the planet's mass all the way up. Whoa! And look at that. Now the amplitude's way up at 300. Even though we're still at an inclination between 0 and 90. So can I adjust the planet's mass and get that amplitude back down to 30, which was the option A preset? Aha. So here we are with an amplitude of 30 now, just like the original setting, despite the fact that the inclination is not 90, which would be best case, it's 50. So the amplitude alone basically does not tell you how, let's say you already know how massive the star is, like it's the exact same as the sun's mass. The amplitude of the radial velocity curve alone does not tell you how massive that planet is, because you could be at an inclination of 90 with a not so massive planet, or you could be at an intermediate inclination with a considerably more massive planet. Each of those scenarios could lead to the same radial velocity curve, and you won't necessarily know which situation you're looking at, because in real astronomy you can't see this, right? That the planetary system or the solar system could be so far away that the details here are totally indistinguishable. Remember that image I showed you at the beginning of the Keck observatories, the imaging of those exoplanets? That's a very rare photograph. Usually you don't have anything like that. All you've got is your radar gun measurements, essentially, your Doppler Shift data. So you don't actually know whether you're looking at a solar system like this with a not so massive planet, or like this with a more massive planet. All you've got is this data here. So that should help you answer questions 9 and 10. In fact, let me go a little further with question 10. If astronomers typically don't know the inclination, if they don't know if they're looking at it like this, or even close to this, what can they actually say about a planet's mass? Well, think through it like this. If you knew that the inclination was 90, perhaps you could use the radial velocity curve to calculate the mass of that planet. Now, if the actual inclination was something like this, and you still got the same amplitude, then that planet would be calculated as being even bigger. So I think the conclusion I'm arriving at here is, well, let me put it this way. If you just assume that you've got an inclination of 90 and you calculate the mass, that gives you the lower limit on the possible mass of that planet. The planet's mass could be even bigger, because if the inclination was actually this and you produce the same amplitude on the radial velocity curve, you would calculate an even bigger mass for the planet. Okay, so it's going to tell you, it's going to give you, I'm basically giving the answer here, so I don't want to be any more specific than that. Okay, now I'd like to talk about this other parameter here, longitude. Let's slow down this animation speed. It's making me dizzy here. Okay, this is a circular orbit, but if we increase the eccentricity, then there's very clearly a perihelion and aphelion. Now ask yourself, at what point on the orbit is the planet moving the quickest? We know from Kepler's second law, the equal areas, equal times, that the planet is whipping around fastest when it's near the sun. So if you were hoping to witness the greatest spike in radial velocity, you would want to be looking this way. Because if you're looking in this direction, then when the planet is right here, that's when the planet's moving towards you the fastest, and hence the star would be moving the opposite direction the fastest as well. And that's what's going on here. So observe that this vertical bar, which indicates which position on the graph corresponds to which position in the orbit. So right here, again, that's when the planet's moving straight at planet Earth, and the star would then be going opposite, and sure enough, that's when you see a peak in the radial velocity. The longitude here tells you not whether you're looking this way or that way. It tells you this. Are you looking from here or here or here? Different parameter. Again, so inclination is this. Longitude is this. Now, what do you think would happen if we change the longitude so that we're looking, our planet Earth is over here? So if I put planet Earth over here, now check it out. When the planet is experiencing its greatest speed, it happens to be going perpendicular to the line of sight to Earth. So this large speed right here would not be detected using the Doppler Shift method. So it's like we would be losing out on that information. And sure enough, yeah, look at that. Now the radial velocity has gone to 0 at that time. And the peak here is only 30. That would happen, I suppose, when the planet is, let me wait a little bit longer. Okay, now the simulation's too slow. Okay, coming up right here. Okay, so with this longitude, the greatest radial velocity occurs when the planet is here. That's when this planet is basically going straight at the Earth, and the star would be going straight away. And the amplitude there is only 30. But if we put the longitude back to where it was, we can take advantage of the maximum speed of the planet at perihelion. So this is where the planet would be whipping around the fastest, same with the star. And now because of our longitude, the planet's going right at us and the star is going right away. Do you see how the amplitude is almost up at 60 now? Well, it's more like 50. All right, so the amplitude will be affected by the point of view of the Earth, specifically the longitude. You know, are you looking straight at the planet at perihelion or perpendicular to the planet? I hope that makes sense. Yeah, and check out this multiple views feature as well. That's pretty nice. Earth view might be the most important one, although you can also just move this around. Okay, so the orbit view that would correspond to the Earth view if your inclination was 0. If I put the inclination back to 0, then the Earth view and the orbit view are almost the same. So you don't necessarily need all these views to answer the questions. Okay, and I'll just briefly describe what they mean by phase here. Couldn't you use 360 degrees to describe the position of this planet in its orbit? Like if, I'm waiting for, right there. We could call that the 90-degree position. Like if this is 0 degrees, right now the planet would be at 90 degrees, 180, 270. Well, often in math we use radians instead of 180 degrees, and we go from 0 to 2 pi radians. Here they've done it even, they've done something even different and just divided the whole thing into phases from 0 to 1. I think that's what we're looking at here, 0 to 1. So 0, phase 0, I'm going to start and pause right there. And let me give this orbit some eccentricity. Aha, so they've chosen phase 0 to correspond to perihelion, and that would mean that phase 0.5 would correspond to aphelion, or the point farthest from the star. Right about there. Yep, sure enough, 0.5. So it's just a system for identifying where in the orbit the planet is, and that'll show up in some of the questions. And the last thing we need to talk about is noise. So back to presets. Okay, remember all real measurements are subject to noise. When you're using a telescope to gather light from some tiny point in the sky that's millions of light, well, I shouldn't say millions of light years away, let's go with dozens of light years away. There's all this other light coming into the telescope as well, and it's impossible to eliminate all that noise. So there's this little noise simulation here. Now, notice that the amplitude of the curve is 30 meters per second. So you're trying to take accurate data of the star's radial velocity over this range of values from -30 to 30, but all your measurements are subject to noise. And here you can set the magnitude of the noise. So think of it this way. How about this? What if you're a cop with a radar gun and you're trying to accurately determine the speed of a vehicle coming at you? So you point the gun at a car and you see 70 miles per hour pop up on your radar gun. Well, those radio waves aren't just going to bounce off the car you're looking at. They're going to bounce off nearby cars, maybe even trees. So there's going to be some waves coming back that are not from the intended target. And maybe your radar gun says 74 when it's really supposed to say 70. So the noise magnitude is a measure of, the extent of that interference or whatever. So show simulated measurements, right? That's including, so that each of these points represents an actual measurement. It's kind of like a sampling rate. It's not that you would necessarily be continuously measuring the speed. Maybe every 2 minutes you measure the radial velocity of that star. I'm trying to think of an example. I don't know. Let's just keep going with the cop example. Maybe the cop has got his radar gun pointed at a car that's like half a mile away on the highway. And let's say every 2 seconds, the cop looks at his radar gun and his buddy in the squad car writes down the speed every 2 seconds, because maybe the car is speeding up, slowing down, speeding up. So each of these dots represents an actual measurement. You wouldn't be measuring a continuous curve, just discrete, isolated measurements. Now, if I turn off the theoretical curve, are we going to look at that and be able to get information from it? Like, what exactly is the amplitude? Well, right now I'm cheating. I'm just hovering with the cursor and the computer's telling me. But if we didn't have the computer here, can you actually look at this data and discern a meaningful amplitude? It's so spread out, I don't think you could do that. Now, if I decrease the noise, now all the measurements are clustered together much more closely. And then we really could, put our cursor in the middle of the peak, so not at the very top or the bottom, but the middle of the peak, and go over to the left and say, well, that's something like 25 meters per second. And we could get a pretty meaningful answer for the amplitude, as opposed to earlier when the noise was really bad here. And now it's like, well, is the amplitude up here at 40 or is it down here at 10? That's such a broad range, it's basically meaningless. So here's a good rule, I think. Let me go back to not showing simulated measurements. Okay, this actual amplitude theoretically is something like 30, 29, or 30. Now, if the noise is significantly less than that amplitude, let's call it 5. Well, that noise, the plus or minus 5, is quite a bit less than the amplitude. So we can get a meaningful answer. But as soon as my noise starts to approach the amplitude, let's just put it at 15. If the noise is half of what the theoretical amplitude is, now you can see that it's almost impossible to determine an amplitude. So a general rule might be, if the magnitude of the noise is even half of the amplitude, or certainly equal to the amplitude, you would not be able to accurately determine that amplitude. I mean, what if I put the noise all the way up at 30? Then this is garbage. You can't see anything there. And the same goes for the period. they don't actually give you a time axis here, but let me go back to preset. So again, this axis is showing you the phase from 0 to 1. But what if it actually gave you the time in days? We know that it takes 365 days to repeat, so this whole time interval would be something like 365 days. And if your noise is really bad, then you can't even tell when the motion repeats. If the noise is small, then there's a clear pattern. Like, yeah, this is the amount of time it takes to repeat. And you could actually determine the period that way. But with really bad noise, you won't be able to determine the period or the amplitude. So that's a real world concern, right, when you're taking data. So those considerations that I just discussed should help you answer questions 15 and 16. Okay, so some of these are a little challenging. There's a lot of different quantities and vocabulary you need to be familiar with in order to answer some of these questions. So the last thing we should do is look at that chart on page 8 out of 10. Here's the chart, page 8, and the first thing I'll note is the bad typesetting here. You're supposed to decide whether a planet's existence, an exoplanet, is detectable. And your options are yes, no, and maybe. And these three letters are supposed to line up with this column, and this column. So if you put an X, like if you're talking about a planet with a mass of 1/10 of Jupiter's mass, one astronomical unit from the star, you would set these options in the simulator, the Radial Velocity Simulator, and then based on the amount of noise and the curve you're looking at, you would have to decide whether this planet was detectable. If it was, you'd put an X for the yes column. If it wasn't, you put an X here for the no column. And if it might be detectable, you're not sure, you'd put it here in the maybe column. So obviously you shouldn't have more than one X in a row. If you've got two X's, it means you didn't make a decision about whether it is not, or might be detectable. Also here, again, bad typesetting. You have to give a reason for your decision. This column corresponds to amplitude too small, A too small, these words right here. If you think the amplitude is too small to be determined against that background noise, then you would put an X here. And obviously you would only mark that if you chose no, it's not detectable, or maybe detectable. So if you think something is detectable, I guess you would just leave these columns blank, because these rationales are only appropriate if you think the planet is not detectable. So P too big, if the period is too big. Well, what's up with that? Even the Kepler mission that I mentioned, it started in 2009. They retired the satellite in 2018. That's less than 10 years. What if you're studying a planet that has a period of 10,000 days? That's way more than just 10 years. So are the people involved in the study even going to have their jobs that long? Are they even going to live that long? You can only take data for a certain amount of time. I guess there are astronomical studies that take decades, but that's going to involve multiple generations of people probably. So again, if a planet is so far, like let's say the radius of the orbit is 10 astronomical units, we saw that for some of those planets, the orbital period could be in the thousands of days. You might decide that that period is just too long. So P too big would be your rationale for saying no, not detectable. So you're going to have to take all those numbers into consideration. Also remember, I mentioned A too small. If your amplitude is about the same size as the noise, turn off that feature for a theoretical curve. If it just looks like a jumbled mess of dots, then you would say, no, it's not detectable because the amplitude is too small. The amplitude is too small compared to the background noise. Okay, that should be enough to finish this chart. And the second method of exoplanet detection, which turned out to be a more popular or more widely used method, is the transit method. I'll probably do a second video where I talk a bit about that. So the bulk of this lab has you exploring the radial velocity method. But remember, Kepler used, I think, exclusively the transit method, and the same is true of this mission called TESS. So this lab should probably be updated. I think it was written at the time the Kepler mission was being planned or just put into action. And since that time, they've now discovered thousands of exoplanets. Cheerio.